The world of science is constantly evolving, pushing the boundaries of our knowledge and challenging our understanding of the universe. Every day, new discoveries are made, and old theories are tested and refined. This relentless pursuit of knowledge drives humanity forward, leading to technological advancements and deeper insights into the nature of reality. Yet, no field of science is as strange, as counterintuitive, or as awe-inspiring as quantum physics. It defies our everyday experiences and challenges our most basic intuitions about how the world works. It is the science that governs the realm of the very small, the world of atoms and subatomic particles. In this microscopic domain, particles can exist in multiple states at once, and their properties are not determined until they are observed. This realm operates under a completely different set of rules than the familiar world we experience every day. While we are accustomed to objects having definite positions and velocities, quantum particles exist in a state of probability, only taking on specific values when measured. Classical physics, the physics of Newton and Galileo, elegantly describes the motion of planets and the trajectory of a baseball. It provides a coherent and predictable framework for understanding the macroscopic world, the world of everyday experience, where objects follow clear and deterministic paths. It provides a framework for understanding the macroscopic world, the world of everyday experience. From the motion of cars on a highway to the flight of an airplane, classical physics offers precise predictions and explanations. However, as scientists delved deeper into the heart of matter, they encountered phenomena that classical physics simply could not explain. The behavior of particles at the atomic and subatomic levels revealed a world that was far more complex and mysterious than previously imagined. At the atomic and subatomic level, the predictable and deterministic laws of classical physics break down. Particles behave like waves, spreading out and interfering with each other, and waves behave like particles, exhibiting discrete, quantized properties. And waves behave like particles. This duality is one of the most perplexing aspects of quantum mechanics, challenging our understanding of the nature of matter and energy. The act of observation seems to influence the state of the system being observed. This phenomenon, known as the observer effect, suggests that the mere act of measuring a quantum system can alter its state, adding a layer of complexity to our understanding of reality. These bizarre and counterintuitive phenomena forced physicists to rethink their fundamental understanding of reality. The classical concepts of space, time, and causality had to be re-evaluated in light of these new discoveries. Quantum physics emerged as a revolutionary framework to explain these perplexing observations. It provided new mathematical tools and conceptual frameworks to describe the behavior of particles at the smallest scales, leading to groundbreaking technologies like quantum computers and atomic clocks. It is a science that challenges our very notion of what is real, forcing us to confront the limits of our intuition and embrace a reality that is far stranger than we could have ever imagined. As we continue to explore the quantum realm, we may uncover even more astonishing truths about the universe and our place within it. Quantum physics, also known as quantum mechanics, is a branch of physics that studies the behavior of matter and energy at the atomic and subatomic levels. It delves into the very fabric of reality, exploring phenomena that are often counterintuitive and defy our everyday experiences. It is a theoretical framework that describes the fundamental properties of nature in terms of the interactions between energy and matter. These interactions are governed by principles that are vastly different from those of classical physics. Unlike classical physics, which deals with continuous and deterministic phenomena, quantum physics is based on the concept of quantization. This means that certain properties, such as energy, are quantized, existing in discrete units rather than a continuous range. Quantization refers to the idea that energy, like matter, exists in discrete packets called quanta. These quanta are the smallest possible units of energy, and they play a crucial role in the behavior of particles at the quantum level. Imagine a staircase where you can only step on specific steps, not in between. This analogy helps to visualize how energy levels in quantum systems are quantized. Similarly, in the quantum world, energy exists in specific quantized levels. Electrons in an atom, for example, can only occupy certain energy levels and must jump between these levels without existing in between. This is in stark contrast to classical physics, where energy is treated as a continuous spectrum. In classical physics, energy can take on any value within a range, but in quantum physics, only specific values are allowed. One of the most profound implications of quantization is that it fundamentally alters our understanding of the nature of light and matter. Light, for instance, can exhibit both wave-like and particle-like properties depending on the experimental conditions. In the quantum realm, the distinction between waves and particles becomes blurred, giving rise to the revolutionary concept of wave-particle duality. This duality means that particles such as electrons can behave like waves, and waves such as light can behave like particles. This duality is one of the cornerstones of quantum physics and has profound implications for our understanding of reality. It challenges our classical intuitions and opens up a new world of possibilities in the realm of science, leading to advancements in technology and our comprehension of the universe. One of the most mind-boggling concepts in quantum physics is wave-particle duality. This concept has puzzled scientists and philosophers alike for decades, challenging the very foundations of our understanding of the universe. It states that particles, like electrons and photons, can exhibit both wave-like and particle-like behavior. This means that under certain conditions, these particles can act like tiny, discrete packets of energy, while under other conditions, they can spread out and interfere like waves. This duality challenges our intuitive understanding of the world, where we typically categorize objects as either waves or particles. In our everyday experience, we don't see objects behaving in such a dual manner, making this concept particularly difficult to grasp. The classic experiment that demonstrates wave-particle duality is the double-slit experiment. This experiment has been a cornerstone in the study of quantum mechanics and has provided profound insights into the nature of reality. In this experiment, a beam of electrons is fired at a barrier with two slits. The setup is simple, yet the results are far from straightforward. If electrons behaved solely as particles, we would expect to see two distinct bands on a screen behind the slits, corresponding to the electrons passing through each slit. This is what classical physics would predict. However, the results of the experiment are astonishing. Instead of two bands, something entirely unexpected occurs. Instead of two bands, we observe an interference pattern, a series of light and dark fringes on the screen. This pattern is characteristic of waves interfering with each other, suggesting that the electrons are behaving like waves. This pattern is characteristic of waves interfering with each other. It indicates that the electrons are not just passing through one slit or the other, but somehow through both slits simultaneously, creating an interference pattern. It's as if each electron passes through both slits simultaneously, interfering with itself. This self-interference is a hallmark of wave behavior and is one of the most perplexing aspects of quantum mechanics. The double-slit experiment demonstrates that electrons, which we typically think of as particles, also exhibit wave-like behavior. This duality is a fundamental aspect of quantum objects and has profound implications for our understanding of the microscopic world. This duality is not limited to electrons. It has been observed with other particles like photons and even molecules. The fact that such a wide range of particles exhibit this behavior suggests that wave-particle duality is a universal property of quantum systems. The double-slit experiment highlights the inherent strangeness of the quantum world, where the act of observation seems to influence the state of the system being observed. This observer effect adds another layer of mystery to the already enigmatic nature of wave-particle duality, making it one of the most fascinating and challenging concepts in modern physics. Another bizarre feature of the quantum world is the concept of superposition. In quantum mechanics, a particle can exist in multiple states simultaneously until a measurement is made. Imagine a coin spinning in the air. It's neither heads nor tails until it lands. Similarly, a quantum particle exists in a superposition of all possible states. A famous thought experiment illustrating superposition is Schrödinger's cat. Imagine a cat inside a sealed box with a device that has a 50% chance of releasing a lethal poison. Until we open the box, the cat is in a superposition of being both alive and dead. The act of opening the box and observing the cat forces it into one state or the other. Schrödinger's cat, while a thought experiment, highlights the counterintuitive nature of superposition. In the quantum world, objects exist in a probabilistic state, and it's the act of measurement that forces them into a definite state. This concept challenges our everyday experience, where objects have definite properties regardless of whether we observe them or not.